I'm going to share a PowerPoint. All right, let me know if you can see my screen and the PowerPoint window.
Yes.
Okay, awesome. All right, so hey everyone, my name is Patrick Fedigan, and I am a professional architect and developer with a large enterprise software platform based out of Santa Clara, but I currently live in Los Angeles. California born and raised, love computer science, went to school for it, so brushing up on topics again. So PageRank is one of my favorite algorithms. It's the one I'll be presenting today. So what is PageRank? What is the problem it's trying to solve? So how do you best rank 1.8 billion web pages in the World Wide Web? So before PageRank, search engines would just search off of keywords and algorithms like grep. So you can just, but this was a problem. So because of repeated keywords, no quality measure, there were many different search engines. It was unreliable. So PageRank was that solution to solve this problem with a quality-based ranking system, relevant and trusted results. So that's kind of like an image of what it looks like, and using a lot of what we learned here in this class, like graphs, directed graphs, um, and some search algorithms. So the history of PageRank is very famous. The two Google founders, Larry Page, developed PageRank at Stanford. They have a public citation or PageRank pa paper on it that I really recommend you reading. It's very short, succinct. It's very well written. So then they actually founded Google, and PageRank became their core technology with it. So it represents a vote of confidence. When you search for a page and you know if it's at the top, it's a confident result because a lot of other pages in the World Wide Web link to it. So, fun fact, PageRank is actually named after Larry Page and not web pages. So, all right, I promise I'll be short. The random surfer model. So this was their core concept. So when randomly searching the web, what's the probability you'll end up on any given web page? Uh, that's what they were, trying to model. So you can picture the web as a directed graph with pages and nodes. The edges are going to be the hyperlinks between the pages when you click on one and go to another one. And then each page will have a probability, so the likelihood of visiting that page. So important pages that have a lot of votes or links will make it more important than other pages. That's the core concept. So three things, part of the algorithm. It's very elegant. It's initialization of the page's ranks, iteration of the PageRank algorithm, and then convergence on those values. That's it. So this is pulled out directly from the paper. You start with the vector of PageRanks at step 0. Then you calculate PageRank values with matrix multiplication via a transition matrix with outgoing node values. You measure how much it's changed. Then you add back in some correction, what we call damping, which I'll go into a second. And then you recalculate with some of that correction values and some randomness. And then you keep looping over that matrix calculation until you reach a tiny threshold, for example, 0.001. And then you stop when it becomes very small. That's it. So the mathematical part of it is this is a representation of how to calculate one node's value at a single step. So you have your damping factor, typically 0.85, which is what they found as a good measurement to add in a randomness factor. So we avoid some problems, which I'll talk about in a second. Then you have those other variables, part of a single step calculation. So it's the sum of all the outbound links. I have it exactly worded in my notes, but it's pretty much the sum of all the outbound links divided by the weight of those outbound links divided by the number of uh, out outbound. Yeah. Sorry about that. And then further breaking down the problem a little bit more, you can actually represent it as matrix eigenvector as an eigenvector problem with a lot of eigenvalues. I'm not a whiz at linear algebra, but I do understand it in this implementation context. So this is also modeling the math part of it, where you can calculate R, which is the new set of page ranks via this core matrix multiplication here with the transition matrix and then the page rank vector. So to continue on, this is a simple animation of what it looks like as you go through each calculation, starting with a graph. It'll over time adjust the weight or the page rank of each page. And then let's actually go through a simple calculation step. So you have your three-node network, an adjacency matrix and a transition matrix, with transition matrix being dividing the out degree. So that's the difference between the two matrices. And then you use that transition matrix as part of the core multiplication step. So you start with each rank, which is the node, the page divided by the total amount of pages. So if there's only 3 nodes, you start with 1 out of 3. Then you multiply that by the transition matrix to get the initial ranks, and then you apply damping to it. So that 0.85 times that multiplied matrix plus the randomness factor to give us the results for this first iteration. So that's it. Then you get the results after the first iteration for this specific node network. You get C is 0.475 probability, A is 0.333, and B is 0.192. All right, let's take a look at the code implementation. Can you still see my screen, or is it showing? Let me. Okay. You can see visual code right now, right? Or
Yes.
okay. So real fast, the core part is this calculate function here, where you have your transition matrix that I was talking about. The core part are these loops right here, where you calculate that sum with the outbound ranks and the transition matrix, and then you add it to the new sum. So let's go ahead and run this. I do have just some iteration or some visualizations in the terminal. So I'm running this algorithm. We have a simple 4-node network. You can see the adjacency matrix here. And after 23 iterations, these are the page ranks that have been calculated. So the top 3 are C, A, and D. Next one, we have actually a separate example with the damping factor at different values. So 0.0 would actually, or 0 damping would actually still multiply everything by 0 and keep our initial page rank of 0.25 for every node. Damping factor 0.85 will give us our normal value, and then damping factor of 1 will actually remove randomness and just kind of even out even more the page rank scores. We continue a 6-node network, took 74 iterations. This one is a little bit different weights. You can see A and C are very highly weighted based on this structure visualization here. And then dead ends. The reason why we have damping and some randomness is because sometimes we have dead ends if there's just pages out there that don't have any ingoing or in degrees. So you can see that's weighted very low. And then finally, circular loops. You can have a circular loop graph, and they'll actually even out all the PageRank scores as well in a perfect circle. And then that's it. That was just a little simple demonstration on the terminal there of different scores. So let's go back to the slides to finish up. Uh, sure. Okay. Time complexity. Normal case is just k times n plus m, which is the number of nodes plus the number of edges. Worst case is n squared with a dense graph. So again, dense graph is when there's lots of edges. Space complexity, O of n plus e, very, very simple. Uh, Benchmark results, you can see how it kind of scales. Scales very nice in a linear fashion with execution time and number of nodes. Um, Practical applications, obviously Google uses it as part of their web search for ranking pages, academic citations, which was their original use case, I believe, to rank importance of research papers. Social networks use it, recommendation systems, biology, medicine, fraud detection, anything with graphs, pretty much, traffic, transportation. Challenges, there are some challenges that I mentioned that with the damping and randomness that fixes that. So if there's sections of graphs and link farms or there's dead ends, um, and link spam handles that pretty well via, it'll even itself out. So you can't just link your page with 100 other pages that don't have any other incoming weight to them. So, all right. And then just finishing up here. Mm, Modern solutions. Yeah, again, some more solutions using this. Key takeaways. Still relevant today. It's a very efficient implementation if you ever take a look at it, very nimble. Has a huge impact. It's considered the trillion-dollar algorithm. Um, and the mathematics behind it are very solid. So just closing thought, the best algorithm is the one that not only works, but fundamentally changes how we approach the problem. Any questions?